Um, Basically last lesson. First, can we go over half-lives, how to calculate them?
Yeah, to calculate it, it's just the formula. So do you remember what a half-life is?
The measure of half the atoms in an unstable isotope and how long it takes to decay.
Yeah, perfect. So the formula to calculate the half-life of an atom is just, well, so what is it? Is it the actual formula you're confused about, or like subbing it in?
Well, one of the homework questions,
Mm-hmm.
I had trouble with. I was trying to use the formula, but I couldn't really figure out how to.
All right, no problem. Let me just get that up quickly. All right, so you left, what one was it? Yeah, okay. So for this question, I'll just get out my whiteboard. Hopefully this works. Yep, works, cool. So for this question, essentially you're told that a substance of 1 kilogram, so I'll write down the formula. The formula is NTNO half to the N. And we're told that NO, the number we're starting off with, is just 1 kilogram. N, well, we kind of have to find what N is, but we're told that the time is 3 minutes and 15 seconds. So I'm just going to write 195 seconds. So we're told that the half-life, so I don't know, half-life is actually 30 seconds. So you have to figure out how many half-lives occur in those 190 seconds.
Right. So that's around 6.5.
It would just be 6.
Oh, okay.
Yeah, because like if you talk about a half-life, well then that's a quarter half-life. It doesn't really work like that.
All right. Okay.
So it's just 6. So that means that this is just going to equal half to the 6, which is just going to equal 1 on 64. So whatever that is. Um, 0.0, how many sig figs? We'll go to 3. 156 kilograms. So 15.6 grams are left in 3 minutes 15 seconds.
Okay. Could we do some more questions like that?
Okay, sure. Were there many in the text? Oh, you did everything in the text, didn't you?
Yeah.
Okay. All right, I can find you some half-life questions on the internet. Just send them across. All right, here is a list of problems. I will send them across.
Okay.
There you go.
Yeah.
So do you want to do these, or do you want to keep moving on with the content?
Actually, I've got a lot more I'm confused on.
Yeah, sure.
Give me a sec. There was also that energy levels problem question.
Yeah, so that is by the Aufbau principle. Do you remember what the Aufbau principle is?
That electrons fill in the shells with the lowest energy levels first.
Yeah, and so what that means is by the Aufbau principle, each shell can only hold a certain amount of energy.
Okay.
That means that when you add electrons, there's once the energy of the electrons hits the energy capacity of the shell, it has to start a next shell where the electrons will fill in the lowest energy level on that.
Yeah. But then I get confused with like the orbitals and all that.
So the actual SPDF notation itself.
The orbitals. So like there's shells, but there's also orbitals. I don't really get that.
The orbitals are, you're only going to need to look at the orbitals when you talk about SPDF. Every other time, you're going to be talking about shells.
Okay.
Yeah, because it's really hard to actually talk about SPDF because you have to get, it's more of a physics thing than rather a chemistry thing. So you just kind of let it be and talk about the Bohr model, for example.
Right. So like just orbitals and SPDF. Is it just this that's in the
Hello?
Hello?
Can you hear me?
Yeah.
Yeah, I can hear you. Yeah, what were you saying, sorry?
So like is it just going to be like orbitals and SPDF and that's it for the content, or is it going further?
No, like everything that's in there is it. It's that it's not very comprehensive. Like there's not much that you can be asked about SPDF, rather than draw it, write it. That's it.
Oh, all right. Okay, and last one. Actually drawing the diagrams of the SPDF.
Yeah.
Um, for the 2p to the power of 6.
Yep.
Why do we only draw one arrow in each box going up rather than both?
So that is by the Aufbau principle. So remember, the Aufbau principle states that electrons fill the lowest level first, and all the up arrows are lower energy than all the down arrows.
Right.
So you have to fill up all the ups before you can do all the downs.
Okay. But why is there only one arrow in each box? Because it's p to the power of 6. Why don't we draw the down arrow?
Oh no. Remember the superscript, so the 6, the arrows you have. So like for your question, I think you put oxygen. Let me get to that last one. And by the way, everything is actually fixed for the homework, so you can just do it in there normally.
Oh, okay.
Oh, actually, yeah, I see the issue that you have now.
Yeah.
So oxygen is right, where you have 2p to the 4. So you see how you drew 4 arrows?
Yeah.
But on the next one for krypton, when it was load, for krypton, what did you do? Firstly, for 3d10, you should draw the arrows, like downwards.
Downwards.
Yeah, because it's a full shell.
Okay.
But can my computer cooperate with me? But for the second one that I'm looking at, I have to adjust your mark. So it's 3d to the 10. So there should be 5 arrows up, 5 arrows down, and then there also it should be 4p to the 3, or is it 6? Hang on.
It's 6.
It's 6. Well, then you should also have all 3 up and 3 down.
Okay.
Does that make sense?
Yes. Wait, so for the 2p to the power of 6,
Yep.
I wrote an upwards arrow only in each box.
Yeah, it should be upwards and downwards.
Upwards and downwards.
Yeah.
Okay, and that's same for like 3p to the power of 6.
Yes.
Yes.
Yeah.
Oh, okay.
Because the number of arrows should correspond to the superscript.
Yeah. No, because I wrote down what was in the book,
Yeah.
and it only had the upwards arrow for 2p to the power of 6.
Yeah, but it wasn't 2p to the power of 6. It was only 2p to the power of 4 in the booklet.
Oh, okay.
So if let me go to it, because I think I'm right from memory, but I just want to double check. So yeah, so you see how nitrogen, how it has 2p, but there's 3. So I'll share my screen this time over here. So you see how nitrogen is 2p.
Yeah.
So we draw the 3 boxes, but if you go by the superscripts, this is 2, 2, and this is 3. And that is what nitrogen is. It has 7 electrons. Does it? Yeah, 7 electrons. So therefore, it's going to have 1, 2, 3, 4, 5, 6, 7 arrows.
Yeah. Okay. I just got really confused by that.
That's okay.
Yeah, okay, I understand now.
You sure?
Yes.
All right, no problem.
Cool.
Would you like me to find some extra questions?
Yes.
All right, I'll do my best quickly. So what are you currently up to at school?
In chemistry at school, because we started year 11, we're just doing revision from year 7 to 10.
Mm-hmm.
Right now, we're just revising on acid-base reactions.
Okay.
Yeah.
Okay, here's 27 questions, but it's a website rather than a PDF.
Okay.
So that might be a little bit annoying for you, but I guess whatever, I guess.
Yeah.
There you go.
All right. Thank you.
No problem. So what are we going? Do you want to continue work, or do you just want to spend time on this?
We can continue.
All right, no problem. All right, cool. So we left off last week. I think that we also looked at the models of the atom, yeah?
Yeah.
Okay. How confident are you with the models of the atom?
I mean, I'm confident in it.
Okay.
It's models, so.
Because everything is fine until you get asked to explain what the emission spectrum of an atom is.
Ah.
So could you tell me what the emission spectrum of an atom is?
It's basically like the amount of energy released by when electrons move shells is something like that. Like it's shown by like different wavelengths of light.
A bit more.
Yeah.
Do you want to know what it is?
Yes.
Okay, so I have this ingrained in my mind. All right. So when atoms are heated, that energy has to go somewhere. So that energy typically goes to the electrons. So when electrons get excited, they move up to a higher energy shell. But however, due to the law of conservation of energy, energy must be conserved. So eventually, these electrons are going to release that energy to get back to their original shell. And they're going to release that energy in the form of light. And that light is going to have a specific frequency. And that frequency of light, or the color we see, is the emission spectrum.
Okay.
Does that make sense?
Yeah.
Okay. Anything else?
No.
Did you end up seeing the flame test or no?
I did. Yeah, watched a video on YouTube.
Mhm.
Yeah, so it's kind of cool.
Yeah, it is.
Yeah.
Yeah, that pops its head up again multiple times actually. So here, module 5 and then module 8. So you're going to have to know those colors off your head.
Okay.
All right, so anyway, we will continue. I think we're getting towards the end. I think this is only 6 lessons, but so this lesson is going to be very theory heavy. So we're going to be looking at different periodic trends. So like we know that we kind of know what the groups in the periods tell us on the periodic table. We know that the group, so the column, indicates the number of electrons in the valence shell and what charge that ion is. Whilst the group tells us how many shells there are. But however, the position of elements on the periodic table, there's actually other trends. And these trends, as you can probably tell in the subdot points, are electronic configurations and atomic radii, which is just plural for radius, first ionization energy and electronegativity, and the reactivity with water. So, you will never be asked to calculate anything. This is just a theory dot point. And what they like to do with this theory dot point is they like to ask you to compare those sub dot points between two different elements.
Okay.
So firstly, we have atomic radius. So the atomic radius of an element is going to be defined as, well, in the image here, either the distance between half the distance between the centers of two atoms, or the distance between the nucleus and the valence shell.
Okay.
I think that just kind of makes sense.
Yeah.
So here is where all the, not confusion, but all the heavy theory starts. So if we go from left to right across a period, the atoms are going to have more protons and, well, hang on. No, they have more protons and they have more electrons, but they have the same amount of electron shells.
Yeah.
So that means that if we go left to right, there's a stronger attraction between the nucleus, where the positive charges are, and the valence shell, where the electrons are. So therefore, the atomic radius decreases because these get attracted towards each other.
Oh, okay.
Yeah.
So, okay.
But if we go down a group, well, we have more shells. So that's just going to mean that the atomic radius increases.
Yeah.
Any questions about
Uh, so from left to right, when comparing hydrogen and helium,
that? Mm-hmm.
helium has a lower atomic radius.
Yes.
Yes. And
Yes.
then helium to neon, neon has a higher atomic radius.
Yes, because it has an extra shell.
Right, okay. It has more shells, so more shells mean higher atomic radius.
Yeah, bigger the atom.
Yeah, okay.
But the further right it is, the more the nucleus and the valence shell are attracted, so they get smaller.
Yeah, okay.
Okay. Electronegativity. Electronegativity rears its head all the way until the end. So this is kind of your little introduction to it. So the analogy that I like to use is that electronegativity is like the bully that steals lunch money from the other kids.
Okay.
So essentially, the more electronegative an element is, the more likely it is to attract electrons from other atoms.
Yeah, okay.
So an example is, well, what element is going to be more likely to attract an extra electron? Fluorine or hydrogen?
Fluorine.
Why?
Because it needs to gain electrons to get a full valence shell.
Yeah, so fluorine just needs one more to be happy and be stable, whilst hydrogen needs 7 more. So
Yeah.
we say that fluorine is more electronegative than hydrogen
Okay.
because fluorine is stronger. It can bully hydrogen, for example.
Yeah.
So what does that tell us? Well, that tells us that going across, so going from left, going from left to right, electronegativity is going to increase, but going up, down, electronegativity decreases.
Okay.
So the reason why electronegativity decreases if you go down is because when you go down the groups, down the groups, you get more shells.
Yeah.
So that makes it kind of harder to get an extra electron when you have like 5 shells compared to 1 extra electron when you only have 1 shell.
Okay.
Yeah. So like my analogy for that is like the elements that are much lower, they have more shells, so therefore they've kind of stolen everyone's lunch money. They don't really want it anymore.
Okay.
They're crappy analogies, but they kind of work.
Yeah, they work.
Okay. So. Okay. Yeah. Cool. And then any questions?
No.
Okay. So ionization energy goes hand in hand with electronegativity. So the more electronegative is, the more ionization energy it has. And it's kind of the exact opposite of electronegativity. So electronegativity is how likely it is for an element to strip another element of electrons. But ionization energy is how much energy is required to take away one electron.
Okay.
So for example, what's going to have more energy? So what's going to have a higher ionization energy? Hydrogen or fluorine?
Hydrogen.
Why hydrogen?
Because it wait, hang on.
Which one's easier to strip away? 1 electron from hydrogen or 1 electron from fluorine?
Hydrogen.
Fluorine.
Oh.
Wait, did I say easier or harder?
Harder.
It's fluorine.
Oh, okay.
Yeah. So picture it again like the bully. The bully doesn't want to lose their things, I guess.
Yeah, okay.
And the reason why I pick hydrogen and fluorine is because hydrogen bonds with a lot of things. And hydrogen very easily forms a +1 ion, doesn't it?
Yeah.
So doesn't that mean the hydrogen very commonly loses its 1 electron?
Yeah, it loses well. Fluorine needs to gain.
Yeah. So fluorine has a higher ionization energy than hydrogen.
Okay.
Yeah. So it's the exact same with electronegativity. So if we go across, so left from right, it increases. But if we go up from down, it decreases.
Okay.
Because the bully is going to hold on to 7 electrons, much more than he can hold on to 49 electrons.
Yeah.
Does that make sense?
Yeah.
Okay. Then the last one is the state of matter at room temperature. So generally we can actually we can guess kind of what the state of a certain element is at room temperature depending on its position in the periodic table. So the general rule of thumb is that all of the metals generally are solids.
Okay.
Yeah. However, there are some, whilst generally all of the non-metals are gases. But however, there are some that are liquid. So the most famous liquid at room temperature is mercury.
Yeah.
Now, mercury is a metal, as we all know, but it's liquid at room temperature, and I think it has a freezing point at like minus 39 degrees, something like that.
Oh, wow.
So I don't really, yeah, like this one kind of, everything's like nice and makes sense, but I don't understand why they asked this one. But so the trend is metals are generally solids, gases are generally liquids. Non-metals are generally gases. Yes.
Okay.
And then if you can kind of remember the 5 exceptions, you'll be sweet.
All right.
And that's it.
All right.
So do you have any questions about anything we've covered so far?
What? In the textbook, I'm looking at the textbook. What's ionization? Like the first ionization. Ionization.
So this is, but the first ionization energy is just how much energy it takes to remove one electron. Whereas
Okay.
the second ionization energy is how much energy it takes to remove the second electron.
Oh, okay.
And you can imagine that removing 2 electrons is going to have more energy than removing 1 electron.
Yeah. Okay. Yeah, that's it.
Okay. And the final trend is the reactivity with water. So reactivity in general. And it's regarding metallic character, which is kind of just like, well, you remember when we looked at the physical and chemical properties of metals?
Yeah.
If something possesses those properties, then it has a metallic character.
Okay.
Yeah. So, so it's just the trend for metals. So going from left to right decreases the metallic character of an element. Well, because on the right side of the periodic table, there's metals. So of course, going from left to right is going to decrease it.
Yeah.
All right. And then going down a group increases the metallic character. So what that means is like, well, when you go down the periodic table, you typically get the elements that you typically associate with metals. So for example, calcium is actually a metal, it's an alkali earth metals, but gold, silver, lead, iron, they're all below calcium. So we say that gold, iron, silver, platinum, they all have greater metallic characters than calcium.
Okay.
Does that make sense?
Yeah.
Okay. So this goes hand in with its reactivity, but more specifically its reactivity with water. So that just means like how I'm reading, how vigorously an element reacts with water. So just like how rapidly and extreme the reaction is.
Yeah.
So that trend is actually the exact same as the one for metallic character.
Okay.
So what does that mean? Well, if you go from left to right, that decreases the reactivity with water. But if you go down, it increases the reactivity with water. So like one of the reasons why in America you can only bring so much water onto an aeroplane. Have you heard about, well, in airports in general, have you heard about that?
Yeah.
The reason why is because some of these elements react so vigorously with water that you only need like 50 mils.
Oh.
Yeah. So for example, I think it's called francium. Francium explosion. Here we go. So I'll just kind of share my screen and we can just kind of take a squiz at this in the meantime. But like, this is an example of a francium bomb that went off in the ocean somewhere in Europe. I'm not entirely sure. But like, they just look at it.
Oh, wow.
Yeah. So, and they didn't really, like, I don't really think they put that much francium in the water, in all honesty.
What?
Yeah. So you can imagine how well, just chucking francium in a bottle of your water that's going to make the aeroplane blow up, basically.
Yeah.
And francium is one of the lowest of the periodic table.
Oh, wow.
Yeah. So francium is all the way to the left and all the way down. So it's one of the most, it's the element with one of the highest metallic characters, and as such, it reacts with water stupidly well.
Yeah.
Yeah.
Okay.
And that's kind of it. There are some rules, but so like essentially the rule is aluminum doesn't react with water, and then you have some elements that react with steam instead, because steam is hotter than water, so therefore has more energy, I guess.
Okay.
And then below that is just kind of like a diagram showing the trends. So that's pretty nice and easy to remember.
Yeah. Okay.
Do you have any questions?
No.
Okay, cool. There's a concept check on the next page.
Yeah.
What question are you up to?
I'm just finishing question 4 now.
All right.
I'm done now.
All right, cool. Do you want to go through your answers?
Yep.
All right, cool. So ionization energy and electronegativity of calcium and fluorine.
So fluorine ionizes energy and is more electronegative than calcium because it requires one electron to gain a full valence electrons, whereas calcium needs to lose electrons rather than gain electrons to have a full valence shell.
That's really good. Yep.
Second one. As the atomic radius increases, the electronegativity and ionization energy increases.
Yep.
Question 3. Metals tend to lose outer valence electrons, while and metals have a higher reactivity than non-metals, and metals are generally found on the left side of the periodic table, and a majority of metals are solids. Non-metals are found on the right side of the periodic table, and they tend to gain electrons rather than lose electrons. And they're usually gases or liquids.
Yep.
Yeah. Question 4. Sodium is more reactive because as you go down the periodic table, the reactivity of each element increases. And question 5. As electronegativity increases, an element's reactivity decreases and vice versa.
Yep. Yeah, the questions are pretty stock standard. Like not stock standard, but like they're pretty repetitive. If you understand the general idea, everything falls into place.
Yeah.
So all you really have to do is know what those two, well, 4 things are.
Yeah.
Yeah. All right, so you ready to move on?
Yes.
Okay, cool. All right. So now we're going to move on to allotropy. So this is meant to be the last thing for the lesson, but because we will actually think that we might even finish this module today, which is pretty cool. So what is allotropy? So this is very short. So allotropy is just basically the property that certain elements have where the atoms can bond in different ways, resulting in different substances.
Okay.
So the most common, well, the most famous example of this rather is, what do you call it? carbon, and we can have different types of carbon. We can have diamond, and we can also have graphite.
Yeah.
So diamond is, well, the hardest. Well, you're going to have to know the properties of diamond and graphite and kind of go from there. So diamond is is extremely hard. It's the hardest structure on Earth. And this is because the way that carbon bonds within to form diamond. So if I want, yeah, cool. Let's get this up. So essentially, how carbon atoms are bonded in diamonds is in a tetrahedron. So a tetrahedron is a triangular pyramid. Like that.
Okay.
So I don't know if you're aware of this, but a triangle is the strongest natural substance on Earth, yeah?
Yeah.
So this is made up of, well, 4 triangles. So this is going to be very hard to break. And then furthermore, each one is connected to another, another tetrahedron. And then this is connected to another tetrahedron, and then so forth, so forth, so forth. The whole thing is made out of tetrahedrons. So therefore, it's incredibly tough and durable.
Okay.
So that's why diamond is so hard. Furthermore, diamond is also, what's the word? These bonds are also very hard to break. Well, and they're very hard to break because, remember, it's made up of triangles. That diamond is going to have a very high melting point. What else? And it also doesn't conduct electricity. So this is the introduction to electricity, and electricity is the movement of electrons. I hope electricity, I hope that kind of makes sense.
Yeah.
Okay, so so for metals, for example, so let's do gold, AG, AU, and then like AU, and then like there. These are going to have 2 free electrons because gold has a 2+. And what happens, well, when you pass an electric current through them, these ions are going to start moving. And the movement of electrons creates electricity. So that's how metals conduct electricity, because they have ions that can move freely.
Right.
In this case, well, let's go back to our little diagram with the carbon, please. All right, if we go back to our diagram with the carbon, well, let's think about this. Are there any free electrons for carbon?
No.
Why?
It's not a metal.
Yeah. So because of that, it does not conduct electricity.
Oh, okay.
Okay?
Yeah.
But you're going to be in for a shock. Graphite, which is essentially the lead in your lead pencils, is also made out of pure carbon, and it's composed in hexagons. Are the hexagons easier to break than diamonds?
Yeah.
Okay, so that means that graphite is going to be very soft.
Yeah.
Also, the actual structure of graphite is that it exists in sheets. So this will be a stack of hexagons, this will be another stack of hexagons, this will be another hexagon, this will be another hexagon. So that's how the lead in your pencil works. When you write, this layer is going to rub off. And when
Oh,
it rubs onto the page, creating the charcoal, lead.
yeah.
Okay. What else? Right. This is where I said you're going to be shocked. Graphite actually does conduct electricity.
Wow. What?
Yeah, graphite conducts electricity because, well, this is only bonded to 2 carbons, isn't it?
Yeah.
So it's going to have 3 electrons elsewhere.
Right. Okay.
Yeah. Does that make sense?
Kind of.
Okay, the reasons why this actually happens are going to be explored a little bit deeper later.
Okay.
So for now, I would like you to skip this concept check.
Yeah.
I'll actually do questions 1 and 2. We'll skip question 3. And we'll come back to question 3.
All right. Okay. I'm done.
All right, cool. So let's do question 1 together.
Yeah. So allotropy is basically the ability of an element to exist in different forms where the forms have different chemical properties.
Yep.
This usually happens because the elements are able to bond in different ways. And question 2. So the elements are able to bond in different ways, which I said in the previous question, which then creates the allotropes.
Yep.
Yeah, that's it.
All right, cool. So if we move on, so we're going to look at bonding, and I'm going to constantly refer back to graphite and diamond because I think it's important that we actually get them, like we know them fully. So for bonding, Well, the whole idea of bonding is that all chemical reactions are governed by the fact that elements are going to combine together to get a full outer shell.
Okay.
And the main mechanism behind this is electronegativity. So that kind of governs where the electron is going to be going. So another thing that you may want to consider is that everything that has a high electronegativity is typically an anion, whilst everything that has a low electronegativity is typically called a cation.
All right.
Because an anion gains electrons whilst a cation loses electrons.
Yeah.
Okay. So the first one we have is ionic bonding. And ionic bonding is typically between a metal and a non-metal. And so in this, well, the metal atom is going to become a cation, typically, if it loses an electron. Non-metal electron is going to become an anion when it gains an electron. So obviously these positive and negative are going to combine to create an ionic compound. So why does ionic compound, or how does ionic bonding occur? Well, ionic bonding occurs between elements that have a high difference in electronegativity. So for example, hydrogen and fluorine, they're on opposite sides of the periodic table. So that would be an ionic bond. Hydrogen and chlorine, they're on opposite sides of the periodic table. Therefore, it's an ionic bond. What about nitrous oxide, NO? Well, they're right next to each other. So do you think it's an ionic bond?
No.
Exactly. So if that, I beg your pardon?
Oh, no, I was just agreeing with you.
Okay. So if there is a small difference or negligible difference, then we have a covalent bond. And the difference between an ionic bond and a covalent bond is that in an ionic bond, one element just gains the electron and the other loses it. So we have two different ions. But in a covalent bond, the electrons are actually shared so that each element is able to have a full shell.
Okay.
Okay, we'll look at this a little bit more when we have to draw them. So when we draw things, we draw them in Lewis dot diagrams. So yeah, basically they're the steps. All right, so to draw a Lewis dot diagram for carbon dioxide, we need to find the number of valence electrons of each element in the compound. So carbon both has 4, oxygen both has 6. Place the atom with the lowest electronegativity in the center. That's going to be carbon in this case. And then place the other atoms around it. You're going to arrange it in a certain case, like we can see in the diagram midway through the page. Actually, you're just going to bond them all together. So you can see in the bottom of that page, page 54, like out of 83.
Yeah.
Yeah, like all you're doing is just moving them. So carbon has 4, carbon has 8, and oxygen has 8.
Yeah.
So this is what happens in covalent bonding. So in covalent bonding, wait, where am I sharing? Oh, I'm still sharing here. In covalent bonding, well, they're shared. So this means that carbon gets all of these. So carbon's happy with its 8, but then oxygen also gets 8 and 8 again.
Yeah.
So all of them are happy.
Yeah.
They all share the electrons equally. Okay, but that's not the only type of that's not the only type of bond. We also have ionic bonds. How do you draw the Lewis dot diagram for that? Well, it's kind of on the next page. So what we do, we basically just write the metal as the cation, and then put the full shell around the anion and use square brackets and then just put the charge of the anion.
Oh, okay.
Yeah. So you have to be wary which one is which.
All right.
Any questions?
No.
Okay. So when we go back to carbon, for example, that is what type of bond is that?
That's a covalent bond.
Yeah, they're both covalent bonds. But covalent bonds, they share electrons. So what's up with graphite? How does it have 3 electrons? That's just kind of how it works. It's just a one-off.
All right.
It's the structure of graphite that gives it its unique properties. So graphite is arranged in hexagons. So therefore, it kind of has 3 electrons, I guess.
Yeah. Okay.
But you'll never be asked to explain why it conducts electricity. You'll
All
just be
right.
asked to compare and contrast, because that's what the dot point says. The
Yeah.
dot point says investigate elements that possess the physical property of allotropy. So you're just going to be asked to talk about 2 different allotropes or something.
All right. Okay.
Any questions?
No.
Okay. So talking about like ionic bonding, covalent bonds. Well, in ionic bonds, we know that there's charge. There's a positive and a negative charge. But in covalent bonds, I never said anything about charges because they share the electrons. But what actually happens is that charges actually arise, but not in the way that you think. They're very, very small charges. So this is basically what polarity is. So polarity is a measure of charge distribution. A polar substance is one that has both a positive and a negative end. So a positive end, like for example, NaCl, that's an ionic bond because metal and non-metal.
Yeah.
So the sodium is positive and the chlorine is negative. So we have a positive end and a negative end. Whereas a non-polar substance is one that doesn't have a positive end and a negative end, but it is neutral everywhere.
Okay.
Okay. So what happens in like covalent bonds? Well, in non-polar covalent bonds, well, the key word is non-polar, the electrons are shared completely equally, which means that there's no charge, everything's neutral. And non-polar covalent bonds are very typically substances that are basically elements, such as chlorine gas, which is Cl2.
Okay.
Okay, and that's because, well, if it's a non-polar covalent bond, then, well, if they're shared equally, that means that the electronegativities must also be equal.
Yeah.
Because they have the same tug, so they share them.
Right.
Okay.
Yes.
Almost every other covalent bond, the electrons are not actually shared, and this is because, well, there's a difference in electronegativity. So what happens, so let's look at B in the diagram, the HCl. The atom with the higher electronegativity, so the one on the right, becomes slightly negatively charged because it's going to slightly attract the electrons more.
Yeah.
And that symbol is a del. It's DELL, so del minus or delta minus. It's lowercase delta in Greek. While the atom that has the lower electronegativity, so the one more on the right side of the periodic table, is going to, well, become a slightly positively charged. So it becomes a slight cation, you could put it. And its charge is going to be del plus. And that's going to make the bond partially ionic, but not quite. It's still a covalent bond.
Okay.
So we can see this in the images. We have a non-polar covalent bond, so that's when the electronegativity is equal. So typically between two elements. So they equally share the electrons and there's no charges on the atoms. For a polar covalent bond, where it is a covalent bond, but there is a difference in electronegativity, the thing that would typically become the anion is going to become del minus charged, and then the thing that should be the cation is going to be del plus charged.
Okay.
And then finally, for the ionic bond, that's when we have a very high difference in electronegativity. So there's no sharing. The anion just steals an electron.
Okay.
And we get full charges. So there's no del minus, del plus. It's actually -1 plus 1.
All right.
And we can see this on the next page. So we can see that for a difference in for the difference of electronegativity, if it's 0, pure covalent, low, polar covalent, high, ionic. And the way that you're going to determine what type of bond it is typically by the distance between them on the periodic table.
All right.
So carbon dioxide is a covalent bond, but it's going to be polar covalent because it's not 0.
Yeah.
What about water? What do you think water is?
Water is polar covalent
Why?
because they've got slightly different electronegativities.
Perfect. So because I have slightly different electronegativities, well, there's going to be a low difference, so polar covalent bond.
Yeah.
Okay. And basically we can look at whether something is covalent or ionic or not to figure out its shape.
All right.
So in order to figure out the shape of something, you're going to first determine how many parts are in that atom.
Okay.
And then you kind of just have to go from there, I guess.
All right.
So if it has 2, it's gonna be linear, that's obvious.
Yeah.
If it has If it has 6, it's gonna be octahedral. If it has 4, it's gonna be tetrahedral. But I want to draw your attention to linear, bent, and the trigonal planar and trigonal pyramidal. So the only way something can actually be linear is if there are no electrons free. No electrons free here, because these are electrons, those little green balls. And as they're electrons, well, they're going to kind of repel these, which are also negatively charged, aren't they?
Yeah.
So, like repel, so that means that these are going to be bent rather than linear. So for linear, an example of linear would be like, let's say we were putting carbon in a line. So carbon, carbon, carbon. Well, there's no free electrons, are there?
No.
So therefore, it would be linear. But for CO2, if we go back to the diagram up here, we can see that there's free electrons. So because there's free electrons, they're going to be here. So it's bent.
All right.
Does that make sense?
Yeah.
You sure?
Yes.
All right, cool. There's a concept check on the next page.
All right.
What question are you up to?
Question 4.
Okay.
I'm stuck on what to write for question 6.
No problem. So for question 6, you're essentially just explaining the difference between pure covalent, polar covalent, and ionic.
All right. So basically that mm, oh, I lost it.
What do you mean you lost it?
No, I still don't understand.
Oh, so like, you know, earlier when we looked at pure covalent, polar covalent, and ionic,
Yeah.
it's asking you to explain what they are and how they relate to polarity.
Oh, okay.
Yeah, because polarity is just a measure of the charge distribution in a molecule,
Right.
and we get 3 from that. 3 variables: pure covalent, polar covalent, ionic.
Okay. So it's basically that polar covalent bonds have no difference in charges.
Yeah.
Yeah, and then non-polar covalent. Sorry?
It's not about charges, it's always about electronegativity.
Oh yeah, electronegativity.
Yeah.
And ionic bonds have fast differences in electronegativity,
Yeah.
and that non-polar covalent bonds have slight differences in electronegativity.
Yeah.
I wrote a similar thing for question 4. Is that correct?
Explain. Yeah, they're basically the same question.
Yeah.
I'll get rid of question 4 because, yeah, thank you.
I'm stuck on question 7.
So basically, the first one is a hexagon shape,
Yeah.
and the second is an angular shape. So which one is going to be a covalent bond and which one is going to be an ionic bond? Think about the shape.
The first one's going to be ionic.
Covalent.
Oh.
Do you know why it's going to be covalent?
Because because they're right next to each other. Wait, is it?
Yeah.
Yeah.
Yeah. Oh, actually, hang on. I think they're both, no, they're both covalent. That was the point of the question. They're both covalent, but if you're told that one is a hexagon, but the other is bent, well, the one that has bent is going to have free electrons, isn't it?
Yes.
So does that mean that it's easier or harder to break the bond?
Easier.
Harder.
Harder. Oh.
So that's why it has a higher boiling point, because it requires more energy to break.
Right. Okay. So a bent shape means it's a stronger bond,
Yes.
while
Typically.
yeah. So hexagonal has a weaker bond than the bent.
Yeah.
Okay.
Well, essentially, it just states, well, the stronger bond is going to require a higher energy to boil.
Yeah.
So we can reverse engineer it. So we can see that sulfur dichloride has a higher boiling point. So that means that the bonds must be harder to break. So that means that bent shapes must have higher boiling points than typically than hexagonal shapes.
Right. Okay.
What do you think?
Sorry.
What does that make sense? Like, what are you thinking?
Oh no, I got it. I got it.
Okay. For the drawings, when we go back over the questions, I'll just draw them and you tell me if you got them.
All right.
Because you actually write it down, don't you?
Yeah.
Yeah. So I didn't really think that you could show me. So what do you have for question 1?
So I had ionic bonding occurs between elements with big differences in electronegativity. So typically between metal and non-metal,
Mm-hmm.
and it involves the transfer of electrons.
Yep.
While covalent bonding is when electrons are shared and there are no full charges of the elements of, of the elements being bonded, like ionic bonding.
Yep.
Uh, and then I wrote that covalent bonding can either be polar or non-polar.
Yep.
So polar covalent bonding occurs between elements with no difference in electronegativity, so like the same element, and non-polar covalent bonding occurs between elements with slight variations in electronegativity.
Yep.
Yeah,
Cool.
that's
For the Lewis dot diagrams, here is what I got. So H2O, remember, oxygen's happy and the hydrogens are happy.
I can't see your screen.
Okay, I'll try it again. Can you see my screen now?
Yeah.
Okay, so for water, the hydrogen's happy and the oxygen's happy.
Yeah, that's what I got.
for the sodium chloride, this is an ionic bond. So the cation plus the anion with the full shell and the respective charges.
Yep.
And then for O2, well, it's just happy, happy.
Yeah.
And that's it. Did you get all of it?
Yeah.
That's good.
And for question 3, water was polar covalent.
Yeah.
Sodium chloride was ionic.
Yep.
And the oxide was non-polar covalent.
Good. Yep.
Yeah, so for question 4, it was basically the same answer for question 6.
Then we'll go to question 6. We'll just move on to question 5 at the moment.
Okay. H2O is bent.
Yep.
Sodium chloride is linear.
Yep.
And oxide is linear.
Yep. That's it. So these are somewhat easier ones, but as long as you understand what's happening.
Yeah.
Okay. And what about question 6?
Basically, the large differences in electronegativity creates ionic bonds. Slight differences in electronegativity creates non-polar covalent bonds. And the same electronegativity creates polar covalent bonds.
Yep. Wait, the same electronegativity?
Yeah.
Non-polar covalent bonds. I heard you say polar covalent bonds. I just want to make sure that isn't what you wrote down.
So I wrote down that elements with the same electronegativity create polar covalent bonds. Is that?
Elements with the same electronegativity create non-polar covalent bonds.
Oh, okay.
Yeah. So if it's the same, it's non-polar. If it's low, it's polar covalent. If it's high, it's ionic.
Right. Okay.
They're the differences. Yeah.
Okay.
All right. And we did the last question together, so I don't really need you to read over that.
Yeah.
All right. So now that we know what the different bonds are, we can see the different structures that arise out of these bonds. So the first one is an ionic network. So an ionic network is made up of ionic compounds. But how it works is that there's no such thing as an NaCl molecule that exists by itself. What actually happens is that it exists in a lattice structure. So it exists in a network. So as you can probably see in the diagram, one sodium atom is going to be connected to 6 chlorine atoms. And each chlorine atom is going to be connected to 6 sodium atoms. So the NaCl is actually just the simple ratio. So for every sodium there's a chlorine, but in that salt, they're all connected in a lattice.
Okay.
Does that make sense?
Yeah.
Okay. Ionic solids have poor electrical conductivity because there's no free electrons. And there's no free electrons because all the electrons are kind of stuck in their structures.
Yeah.
And they're also brittle. So they're brittle because if they're made up of alternating positive and negative charges, then all it takes for you to kind of move one layer, so then you have positive, positive, and then they repel.
Yeah. All right.
Does that make sense?
Yeah.
You sure?
Yes.
Okay. Next is covalent network. So a covalent network is like what we're looking at with diamond and graphite. So they're made up of, well, networks of covalent molecules. And they kind of depend on the structure. So that will go back to the allotropy of carbon and diamond being very hard because it's arranged in tetrahedrons, whereas graphite is very soft as it is arranged in sheets of hexagons.
Okay.
Any questions?
No.
Okay. The next one is covalent molecular. So these are covalent bonds that don't exist in huge systems, but exist kind of just like by themselves. Like an example is water.
Right.
So not all water molecules are bonded to each other, for example.
Okay.
Like all carbon atoms are bonded to each other in diamonds, but not all. But water molecules don't bond to other water molecules like carbon does.
Oh, okay.
Yeah. So these are called covalent molecular, and they're held in place by something called intermolecular forces, which we're going to look at later.
Okay.
An example of a covalent molecular structure is ice. So ice typically exists in a lattice that is held together by intermolecular forces, and well, the crystals have low melting points because these forces are weak, like as we're going to find later. And these weak forces also make the crystals soft and malleable and ductile.
All right.
Okay. Next is metallic structure. So this is the actual definition of a metal. So a metal is defined as a uniform distribution of cations within a sea of delocalized electrons. So it means that I have a lattice of cations, like a 3D lattice of cations, and then between all those cations, there's just electrons chilling, just doing their thing.
Oh, okay.
And those electrons are all free. So that's why they're called delocalized.
All right.
And because these electrons are delocalized and hence they're free, that means that they can move, creating an electrical current.
Okay.
That was a lot of theory.
Yeah.
Okay, it's all summarized on the next page.
All in one table, all that theory.
Yeah,
Wow. Okay.
that's why I love this table.
Yeah.
But you will be asked to compare and contrast them and all that stuff. And I'm not going to get you to do this concept check on the next page because we're actually right at the end of the module.
Oh, wow.
We have one more dot point to go.
Okay.
So this last dot point is talking about intermolecular and intramolecular forces. So I like to talk about this in terms of the internet. So there's the internet and the intranet. So the internet, I am talking to you right now over the internet. This is from my computer to your computer, wherever you are. And the intranet is everything that's on your computer. So that's like your local disk drive and stuff like that.
Yeah.
So how does that apply to forces? Well, let's think about it. Intramolecular forces are going to be the forces that are inside a molecule. Whereas the intermolecular forces are going to be the forces that exist between different molecules.
Okay.
Does that make sense?
Yes.
Okay. So what are examples of intramolecular forces? So intramolecular forces are basically it's called electrostatic attraction. So like the electric attraction between positive and negative charges that causes ionic, covalent, metallic, all those different bonds that we've been looking at earlier.
Yeah.
And intramolecular bonds are much stronger than intermolecular forces because, well, let's think about it. What is going to be a stronger force? The force that actually holds the two atoms in place, or the forces that just kind of exist between all the other molecules?
The force that holds the atoms in place.
Exactly. And that's essentially it. But But intermolecular forces, they can also contribute to things such as the melting point, the boiling point, and things like that, because they kind of they give an indication of how much energy is needed to do something.
Okay.
So there are 3 types of intermolecular forces. The first one is called dispersion forces. The technical name is London dispersion forces, but you'll never actually call them London dispersion forces. You'll just call them dispersion forces. So dispersion forces are the weakest intermolecular force, and they exist between all molecules. All of them, doesn't matter. And the reason why these dispersion forces occur is because, well, there's going to be temporary dipoles formed through the movement of electrons. Do you know what a dipole is?
No.
Okay. A dipole is something in polarity. So a polar covalent molecule is an example of a dipole because it has a positive charge and a negative charge.
Okay.
An ionic bond will be an example of a dipole because it also has a positive charge and a negative charge.
Oh, all right. Okay.
Dipole, 2 poles.
Yeah.
Yeah. So essentially, if you, I'll kind of get my screen up. Essentially, there's going to be periods of time where this might become del minus and this might become del plus. And well, if this is del plus and this is del minus, these are going to be attracted to each other. So that kind of holds the substance in place, you can say.
Yeah.
The next one is, oh, well, actually, it has it on the next page, technically. So the next one is dipole-dipole forces. And for dipole-dipole forces, oh, I'm on poor connection. Can you hear me?
Yeah.
Okay, I just got poor connection pop up and I'm just like, uh-oh. But anyway, so the next one is dipole-dipole interactions. So when multiple molecules are in polar covalent or ionic bonds, one side of the molecule is going to be slightly negative and the other is going to be slightly positive. So because there's 2 poles, dipole. And how dipole-dipole interactions work is that the negative dipole is going to attract another positive dipole and hence it's going to put them together.
Yeah.
And this is compared to a London dispersion force where, okay, yes, dipoles do form, but these dipoles aren't permanent. These dipoles are temporary.
All right.
The key word to stress is temporary. So this is the 3rd last line, forming temporary dipoles. And then the last one is a special type of dipole-dipole interaction, and it's called hydrogen bonding. So the strongest intermolecular forces occur between the greatest difference in electronegativity. So if hydrogen bonds with either oxygen, fluorine, or nitrogen, they're going to cause very, very strong dipole-dipole interactions, and this is called hydrogen bonding.
Okay.
And congratulations, that's it.
Wow.
What do you think?
That was a lot of theory.
Yeah,
A lot to process.
don't worry, the next topic is all math.
Oh. Slightly better, but
Oh, okay. It gets better.
okay.
But how do you feel about that? You just kind of completed the whole module.
Yeah, yeah, I feel all right.
Okay. So, for homework, because I just basically do all the questions that we haven't done. The fourth lesson homework is online, and I will release the fifth one probably tomorrow because you did the fifth lesson as well as the fourth lesson.
Okay.
Because like we were kind of like bleeding into the next lesson, but that's okay.
All right.
That's all right. So next lesson, we will probably start the review.
Okay.
We'll start the module review, and well, depending how many lessons we do, that next lesson will be our quiz.
Okay.
And that's kind of it.
All right.
Well, you finished the first module.
Okay.
Do you have any questions? Because that was a huge theory slog towards the end.
No. Yeah, I got everything.
Okay, it's just a lot of stuff to remember.
Yeah.
Okay. But the good part is that this is kind of the foundation. So like probably 80% of the content that we revised today, like the new content, it comes up again and again and again. So it's good.
Yeah.
Like in terms of the trends of the periodic table, they all come up again.
Right. Okay.
Allotropy doesn't. Bonding absolutely does. And then the chemical structures doesn't, not really, but the intermolecular bonds absolutely.
Okay.
So that's kind of it.
All right.
Is there anything you want to do in the last 5 minutes?
Not really.
Okay. Do you just kind of want to look over your work?
Yeah.
All right, no problem. I can let you be if you want.
Oh, okay.
You have to tell me.
Oh, yeah, I'll just look over my I'll just look over my notes and fill up anything.
All right, no problem. Yeah, please message me if you need anything. Everything, yeah.
Yeah. Okay.
All right.
All right.
Bye, I guess.
Yeah.
Yeah.
Thank you.
All right. No problem. See you next week.
Bye.
Bye.